A great smooth wall of silica looms up, perforated by rows of curious symmetrical designs. It's the shell of a microscopic plant found by the billions in seas and fresh water, a diatom. Diatoms have distinctive shapes. This species is Cimbella. We saw minnow-sized fish eating water fleas. What do water fleas eat? Diatoms, like Gomphonemon. Look at this, nature's perfection sculpted in silica, just thousandths of a millimeter long. Seeing nature's wisdom at this level, we begin to understand why computer chips are made of silica too. But that's another story. This realm is one in which strange dome-shaped objects rise and fall like tides beneath a giant moon. Perhaps they're living things growing and wasting on a flat, barren landscape of fantastical design. And let's not get carried away. When human breath fogs up cold glass with water droplets, that's what we're looking at right now in nanospace. At this level, substances change back and forth between liquid and gas. If you breathe on cold glass, it fogs. Step back, and the water evaporates. Breathe on the glass again, and so on.
The array of available electron microscopes gets larger year by year. This one can study changes in the specimen being observed. This sequence records the growth of naphthalene crystals, a chemical used in insecticides. Just as ice evaporates on a sunny day, so can naphthalene. Here, potassium chloride crystals grow. Crystals of different substances grow in very specific shapes. This is because the atoms forming them are laid down in highly specific lattice-like structures. The great bricklayer of the universe never mixes up architectural plans. Each layer in this potassium chloride crystal is about 1/1000th of a millimeter wide, an orderly sequence of atom on atom, the structure of the crystal predetermined by the nature of its chemistry. The atom itself is the smallest coherent material particle, the ultimate goal of our quest into nanospace. Gold, one of the heavy elements. Turning a bar into gold leaf gives us a better idea of the properties of the smallest material things, atoms making up each molecule of gold. A bar starts off about as thick as a wristwatch, 7 millimeters. Each time it goes through the rolling mill, it gets thinner and longer. Before this process is finished, the bar is a ribbon 15 meters long. By this time, the gold, rolled gold sheets, can be cut with scissors. At this stage, it would take 20 sheets to make a stack of gold 1 millimeter high. Next, sheets are put between pieces of paper, and the bundles sandwiched between soft leather. At this point, the gold is beaten even thinner. Even now, the process has only just begun. The sheets are cut up, bundled again, and beaten some more. To put this in perspective, a piece of gold that started as not much bigger than a man's thumbnail is now 2 meters long by 1 meter wide, the size of a single bed. In practical terms, the area of leaf that a gold beater makes depends entirely on his skill. At this point, the gold is 150 billionths of a meter thick, so thin that we can see through solid metal. We are looking right through nanospace. Even the finest craftsman cannot reduce gold leaf to fewer than about 750 layers of atoms. That is the first reason why electron microscopes have trouble spotting one among the many. It's like looking for a needle in a haystack.
Atoms, the principal entity in nanospace, as in the universe, don't easily reveal themselves. In this computer simulation, table salt is starting to dissolve in water. The orange and green balls show sodium and chlorine bondings in the salt. The small red and white ones are water molecules. We're slowing the reaction speed by a factor of perhaps a million times. Even so, atoms are in constant motion. That is the second major reason why atoms are so difficult to find. The third reason is that atoms don't have a solid surface. We refer to them as matter, but an atom is not a physical thing like a nut. Its nucleus is surrounded by a fuzzy cloud of electrons. Finding an atomic surface amounts to surveying the edge of a fog. In other words, seeing an atom involves detecting some thing on the edge of existence, moving at enormous speed and having no physical shape.
A single photograph, 1 in 1,000, bore fruit. The large, bright areas are overlapping clusters of atoms. But Hashimoto's group was chasing a single atom. February 1971. At last, the team managed to capture a single bright blob, the mark of one atom. 380 years after the microscope was invented, researchers detected the presence of the elusive, long-sought atom.
Just 20 years after a film plate gave us the first foggy image of a thorium atom, atom spotting is almost routine. In this pattern, that looks like blue tweed, every bright spot represents a single atom, a screen full of atoms. This image shows a sample of ceramic material. Now watch what happens when I clap. The atoms vibrate in response, all in unison. The sample is encased in a heavy steel microscope, but still it responds. Perhaps each human footstep shifts as many atoms in the earth as there are stars. Never forget, we are in constant touch with nanospace.
We're at the atomic level, among the smallest material units of being. Around me, gold atoms, always in motion, always restless, as you can see. But even though atoms are always moving, as long as the gold is a solid, the atoms pack together in an orderly, crystalline, three-dimensional pattern. Of course, each element and compound has its own particular organization. Here we have two clusters of atoms, several thousand in each, merging into a single particle of gold. We're looking at gold atoms assembling into well-defined, orderly rows, becoming a crystalline lattice of gold. In nanospace, in nature, atoms are in constant motion, as restless as change itself. Here's another tweed-like pattern with atoms drawn up in the rigidly ordered formation that nature intended. In this case, the separate bright and dark patches represent calcium atoms in a human tooth. The jewel among jewels, diamonds. Diamonds result from intense heat and pressure deep within the earth. Under those conditions, carbon atoms are crushed into the lattice which gives diamond its famed brilliance and hardness. The Greek philosopher Lucifer.
Scientific discovery and reward come slowly. Ernst Ruska's work gave birth to the electron microscope in the 1930s. His Nobel Prize for Physics came almost 50 years later, in 1986.